In this video, we're going to look at mass laws, the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. So, the law of conservation of mass. When a chemical reaction occurs, the mass of the reactants is always going to be equal to the mass of the products. Another way of saying this is that matter is neither created nor destroyed in any chemical reaction. And so an example would be that if we started off with 8 grams of oxygen and 1 gram of hydrogen, and they react, well, they will form 9 grams of water. Our 8 grams and our 1 gram gives us 9 grams of starting materials, and we have 9 grams of products. Similarly, if we have 6.9 grams of lithium and 42.0 grams of sodium, they'll react to give us 25.9 grams of lithium fluoride and 23.0 grams of sodium metal. And adding these up, we have 42.0 plus 6.9. This is going to be 48.9 grams of reactants, lithium and sodium fluoride. Well, we get as products 25.9 plus 23.0, and that is going to be 48.9 grams of products. Different products, but still the same amount of mass. There's not creation or destruction of mass in this process. So, the law of definite proportions, that has a few different names. The law of definite proportions, law of constant composition, and also Proust's law, named after Proust. This says that a sample of a compound will always have the same ratio of elements. And that's true in terms of the number of atoms, but back in Proust's day, there was only really mass that we could deal with. They only had balances. They couldn't really see how much individual atoms weighed. So, for example, an example of this is that carbon dioxide, CO2, it always contains 27.3% carbon and 72.7% oxygen by mass. Any sample of carbon dioxide, whether big, small, or anywhere in between, will have this percentage of carbon and this percentage of oxygen by mass. So, if a sample is 10.0 grams, there will be 2.73 grams of carbon and 7.27 grams of oxygen in that sample. And let's say we had twice as much, a 20.0 gram sample, there would still be the same percentage of carbon and the same percentage of oxygen. If I wanted to, I could just multiply by 2, but I could also calculate it by saying, all right, we have 20.0 grams of CO2. We're going to multiply it by the percentage, 27.3, and I'm actually going to take this percentage and I'm going to call it that many grams per every 100 grams. And this is 27.3 grams of carbon for every 100 grams of carbon dioxide. And here we go. That is my conversion factor. We get, well, 2.7. We get 5.46 grams of carbon out of the 20 gram sample. And I'll do the math quickly in my head, but we could use the same thought process. For the oxygen, we'd have 14.54. So it would be 14.54 grams of oxygen and 5.46 grams of carbon. Have I done this correctly? No, I have not, because actually I only have 3 sig figs here, so I'm actually going to have to cut off my 14.54 and just call it 14.5 grams of oxygen. Moving on, we now have the law of multiple proportions, and this is tricky. The law states that if 2 elements can form more than one compound, for example, carbon monoxide and carbon dioxide, Both are made of carbon and oxygen. Very, very different. I'm breathing out carbon dioxide. Carbon monoxide is a very toxic gas. So totally different substances made from the same basic materials, the same basic elements. But if two elements can form more than one compound, the masses of one element that combine with the other are always in a ratio of small whole numbers. This is really difficult to wrap your head around. Ratio of small whole numbers is definitely what you really want to focus on here. So, for example, 14 grams of nitrogen can combine with 8 grams of oxygen. In that case, it happens to be, and you'll get to learn about this later in the course, you'd get to realize, oh, it's N2O would be the formula of the compound. Well, 14 grams of nitrogen can also combine with 16 grams of oxygen, and that would give you NO. 24 grams of oxygen would give you N2O3, 32 grams of oxygen would give you NO2, and 40 grams of oxygen with 14 grams of nitrogen would give you N2O5. Back in the day, it wasn't really clear as to what these formulas were, but there was an understanding that 14 grams of nitrogen could combine with any of these to produce unique compounds. They're all nitrogen oxides, but with different properties and, as they would find, different formulas. So as you inspect this, you can see that the ratio here is that for every, the oxygen goes up in units of 8 grams. So we have 5 times as much oxygen in N2O5 than we do in N2O, and 4 times as much oxygen in NO2 as we do in N2O, etc., etc. We have this going up by 8s. Now, another way of looking at this is, let's say carbon, for example. Let's go back to our carbon monoxide versus carbon dioxide. Now, I happen to know that 12 grams of carbon can combine with 16 grams of oxygen or 32 grams of oxygen. Let's take a ratio here. Let's take our 16 grams of oxygen for every 12 grams of carbon versus our 32 grams of oxygen, if this were right. Grams of oxygen for every 12 grams of carbon. So if we compare the 16 over 12 versus the 32 over 12, it might not be obvious at first, but we have, let's take the 32 over 12 versus the 16 over 12, and what we get is, the 12s cancel each other out, and we get 32 over 16, so we end up getting actually 2 to 1. And when you think about it, this is 2 times as much oxygen in the CO2 as there is in the CO, which makes sense because there's twice as many atoms of oxygen in CO2 as there are in CO. And that would be one way of proving the law of multiple proportion.